Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology in the subject of particle physics with the course code PHY 452. We are at the lecture number 2 and the topic is classical era of particle physics. The subject of particle physics has a long history and it can be divided into many parts and eras. The classical era is supposed to start at 1897 when the particle physics was begun and ends about 1932. In this era, some very fundamental particles were discovered, but later on these particles were discovered to have structure in them, that is, they were composites. But these particles in this classical era actually laid the foundation of the subject. So therefore, it is important to go into the details of this classical era and see that how these particles were discovered and what were the experiments and theoretical understandings at that time. So this lecture would be kind of detour in the history of the particle physics, and we will try to find out two things. The first is what were the theoretical understanding of particle physicists at that time, and the secondly, what were the experimental confirmation for discovery of different particles. So let's start with the view held by Greeks about the matter. So Greeks 1000 years ago were convinced and logically concluded that all matter is made of atoms. So atom by definition means the something which cannot be further divided, something which is not divisible. So the Greeks atomist view was that atom is something which cannot be divided. So they thought about different matter around them, and they thought that whether they can what were the basic building blocks of this matter. So they logically concluded that if we divide the matter, then we can divide it into two parts, and if we go on, then there will be a limit beyond which we will not be able to divide further, and that limiting amount of matter is called atom. That is, the atom cannot be further divided. At that time, it was a very logical point of view, and that was held for 1000 years. When time came, and in 1897, J.J. Thompson was the first one who actually challenged this atomist point of view, started with the Greeks. And this challenge, he challenged it with the his experiment, which is called J.J. Thompson experiment. And what he was doing basically in that experiment was to test that whether in this tube, you can call it a vacuum tube, where the electrodes were installed, and he was trying to test that if there are some kind of rays, let's say cathode rays, which were traveling from positive to negative plate, could be deflected, or they are deflected when there is a positive and negative plates placed there. And he was surprised to know that these particles, I have put there the negative charges, but at that time he didn't know that they are charged particles, till he put these plates over here and performed the experiments, and he found that these rays are deflected towards the positive plate. And from this he concluded that these particles must have negative charge. First of all, they must have a charge, and the second of all is that they have the negative charge because they were deflected towards the positive plate. So from this curvature of these particles, and he concluded that these are the particles, he called them corpuscles, and the charge on them as electron. So at the beginning, the name was given to the charge of these particles was electron, and later on that name was used for the particles themselves. So in this way, J.J. Thompson was able to discover that atom can be further divided, and it is divided into two parts. It has a structure, and the old view of Greeks was challenged and proved to be wrong. That is, the atom is divisible, and we can divide further atom, and basically it is made of two parts, that is the positive charge part and the negative charge part. So by this we call this discovery of electron, we call somehow the birth of the particle physics, the modern point of view of the particle physics, so to say. And it was in 1897 when J.J. Thompson was able to discover electron, negatively charged particle. But after this experimental discovery and birth of the particle physics, the immediate question arose that how the negative and positive parts of the atoms exist, that how they coexist with each other. Where is the negative part and where is the positive part in the atom? But before that, I would like to tell you that in this lecture series, I will also give you the counting of the particles, that how many particles we had at which time in the history. So at that time I would say that in 1897, with the discovery of electron, the counting of the particles, fundamental particles, started, and this electron was the first fundamental particle we discovered, this let's say this electron. And at that time we can say that the total number of fundamental particles discovered was 1. So this was a very simple view, but the breakthrough was that we were able to discover that atom is divisible and it has two parts, and the first particle we discovered was electron. At that moment you will be thinking that why I am not calling the positive charge as a particle. The reason is that at that time the positive charge of the particle the positive charge inside the atom was not considered as a particle. And let me explain this with the idea of the J.J. Thompson himself, because when J.J. Thompson was challenged with the thought that if there are two parts of the atom, one is negatively charged and another is a positively charged, then how these two parts of the atom coexist. So he presented an idea and theory, so to say, of or a model which is called Thompson pudding model. The name pudding was given by himself, and he explained the coexistence of the positive and negative charge by the analogy of a pudding, where he said that the structure of atom is like a pudding, where the positive charge is spread over everywhere inside the atom, like over here you can see. So this is the positive charge everywhere in the atom, and the negative charge, so it's like a pudding, it's like the pudding spread over everywhere, and the negative charge that are the electrons are like the pumps which are embedded in different throughout the atom inside the positive charge. So atom as a whole has to be neutral, must be a neutral entity. So these negative charges and positive charges were cancelling each other, and we seen that electrons were like J.J. Thompson presented electrons like pumps in the pudding, and this pudding model was actually solving the problem of coexistence of electrons, and that is the negatively charged particles, and the positive charge part of the atom, but it had no experimental evidence that it's really like this. So there was another experimentalist and physicist, a very famous one from New Zealand at that time. When he reached Cambridge, where he read about and he studied about this pudding model of J.J. Thompson, so he decided to test this model. And for testing this model, he devised an experiment which is a very famous experiment in the history of physics generally and particle physics particularly, called the Rutherford Experiment. And with this Rutherford experiment, he wanted to test that the pudding model, J.J. Thompson's pudding model, that whether it is correct or not. So he chose to have the thin plates of gold at that time, and then his idea was that if I had got the thin plate of the atom, and positive charge is spread everywhere, as you can see over here, and the negative charge is like these electrons are like pumps embedded everywhere. So he thought, if I could get another heavy positive charge and I bombard it, this atom I bombard it with these positive heavy particles, charges or atoms, then they shall reflect with the smaller angles. So like electrons, some heavy atoms, I mean comparatively heavy as compared to the electrons, if they come over here and deflect, so they will be deflecting with the smaller angles like this, with these angles. But he did not observe something like that. So he was devising the experiment like this, that he got the atom of helium, which is also called alpha particle, which was doubly positive charge, and he bombarded them on the atom, and these alpha particles were coming in this positive charge, and his idea was that there will be some reflections with the smaller angles from the atom, because these are positively charged particles. But he was surprised to see the results, and the results were that when he bombarded this atom, so most of the alpha particles went through and they were not deflected at all, but very few, one or two of them, were deflected from the center of the atom. So he was surprised to know, and he immediately concluded from this his famous experiment, that is Rutherford's experiment. He concluded that most of the atom is empty and there are no electrons inside there, and no positive charge is there, and the positive charge is all concentrated at the center of the atom. Later on it was called nucleus, and he called it this positive charge part is like a proton. So there I would say that he discovered another particle which is a proton, which was a positively charged particle and inside the nucleus. So Rutherford model was like, then he presented his own model, because he proved that the J.J. Thompson model is not correct of this pudding model, that is positive charge is spread everywhere and electrons are like pumps inside this positive charge. So he presented his own model where he said that excuse me, that most of the atom is empty, like you can see over here, and there is a positive nucleus or positive center of this atom where all the positive charge is concentrated, and there is electrons around the nucleus which are spread there. At that time he didn't know that they are circling into the orbit, but he just knew that there are electrons, and which are smaller than the nucleus, and nucleus is the central part. So in this Rutherford model he was able to discover another particle, and if called proton, which has a positive charge, and if we go towards now the discovery of the proton by the Rutherford experiment, and if go towards the atom hydrogen and see how this structure is of atom is there, so you would see that the proton is in the center of the hydrogen atom, and electron is in the around it somewhere, placed somewhere. That was the Rutherford experiment. So from this we conclude that now we have total number of particles equal to 2, that is the electron and a proton, and the total number of particles are 2. So the counting at that time of the fundamental particles reached to the 2. So the basic understanding we got from the Rutherford experiment was that the positive charge is not spread everywhere. It's not like the pudding. It's also like a particle, and this particle was called a proton, and it's positively charged particle. So at that time it was very convincing and relaxing that we now know that atom has two parts. The central part, which is the core of the atom, is called nucleus, and it has got positive charge, and there were electrons which were negatively charged particles, and they were circling around the proton, and so proton and electron charges were balancing each other. So atom was still neutral, it has no charge, but we got the two particles there. So that was very good, and we got particle physics going very well. But immediately after the Rutherford experiment, there was a need to be explained. There were several different problems arose at that time, which I at the moment will not go into detail, but I will give you the hint. For example, the first problem was that how the spectrum of the hydrogen atom could be explained with the help of the Rutherford model, because we got the line spectrum from the hydrogen atom. Different kinds of lines emerge, like Balmer series and other series, as you know, and there were no possible explanation was available. The second problem was from the electromagnetic theory, from where we knew that the accelerating charge particles should radiate and emit energy, and if electrons are moving around the nucleus, they shall radiate and finally collapse into the nucleus, and we should not have a stable atom. But on the contrary, experimental evidence show that we have stable atoms. So these and other many problems forced actually Bohr to give the better model than Rutherford model, and Bohr gave the model that the electrons are circling around the nucleus into fixed orbits like this, as you can see over here, and they do not emit energy when they do not emit or absorb energy when they are in the one orbit. They only emit or absorb energy when they move from one orbit to another orbit. And in the center part of the atom there is a nucleus, and it contains protons. This Bohr model actually was coming from the quantum mechanics. Later on I will in detail explain in later on lectures that what is quantum mechanics and how quantum mechanics emerged at that time, because if you go into the history of the physics, you will see that particle physics and quantum mechanics, they were started almost at the same time, and at the around 1890s and 1900, and they got developed in parallel. So new particles were discovered, and their theoretical explanation, were not available. And at that time, quantum mechanics were in parallel developed to answer many questions coming from the experiments. So this was a very nice journey, the parallel journey of the particle physics and quantum mechanics. So there were experimental discoveries from particle physicists around the world, and there were then theoretical physicists who were explaining that why we should have these particles, how they interact, and all this. And it's still going on, as you might have heard about the Higgs particle at the CERN. Still many experimental discoveries and their theoretical explanations are still open problem. So at that time, Bohr came, and with the help of quantum mechanics, he gave a new model, which is called the Bohr model, which still exists, and to certain limits. And in the school physics, we teach that atom is a Bohr model. and roughly speaking, with a minor correction, is still a very good model which explains the structure of the atom. Anyhow, so at that time the counting, it's like around 1913 that we had the understanding of the atom a little bit advanced. We knew that there are parts of the atom, negatively charged particles called electrons and the positively charged particles called protons, and how they exist inside, and everything was so good. But at that time there was a slightly difficult problem arose with the heavier atoms, when physicists at that time found out that some heavier atoms, for example helium, we could have two protons and we have two electrons, so atom is electrically neutral. But the problem was that you might think that it is two times of the mass of the hydrogen atom, because in hydrogen atom we have one proton and one electron. So in helium atom, in principle, we shall have, since we have two protons and two electrons, it should be the two times heavier than the hydrogen. But on the contrary, people found that the helium is not two times, but it's actually the four times of the hydrogen atom, and it was surprising. And the problem arose that why the heavier atoms, although they are electrically neutral, the problem was not there. Why they are heavier than their corresponding constituents, for example, if you break them in constituents, why they are heavier than them. And this problem was at that time solved by Chadwick's discovery of neutron, who found out that with the experimentally that the nucleus of the helium atom actually contains not only two protons but also the two neutrons, two neutral particles which are chargeless. That's why electrically, or you can say electromagnetically, they are not could not be discovered, or they could not be traced. But if you go with respect to mass and measure the mass of the atoms, then you find out that there are two other one another particle inside the nucleus, which was called neutrons, and Chadwick discovered it. And so we got the counting of the particle now goes to 3, and after the Rutherford experiment, we got the total number of particles now: electron, proton, and neutron. So the total number of counting goes to the 3. So we got now 3 particles, that is electron, proton, and a neutron. So Chadwick discovery made it possible that we have discovered the neutral particle, which had no charge, but at the same time it had mass. So the heavier atoms mass could be explained. So that was the classical era, I would say, where 3 very fundamental particles were discovered, that is electron and proton and a neutron. That was a very satisfying time for the particle physics, when particle physicists knew everything. They knew that the atom is made of 3 particles, and how they live together, what is the structure of the atom. So everything was okay. Everything was matching the theoretical predictions. The theory and experiment were going side by side, and they were helping each other. So that was a very good time. But soon after that era, physicists came to know that this is not the end, but it's just the beginning, and there were new problems arose, new types of particles arose which could not be explained, and new discoveries of the particles started. So this our journey have just now begun, and we will see that there are about 64 fundamental particles. Actually today's 3 particles, 2 of them are actually not the fundamental particles, like proton and neutron. Later on we will find out that these proton and neutron are actually not fundamental particles. Only electron is included in the list of fundamental particles which we accept today, and proton neutron are not fundamental particles. They are actually made of quarks. This we will see later. But as I told you in the beginning, that this lecture series is like a detour into the history of the particle physics. So imagine yourself that you are now sitting around 1930, and you just know that there are three fundamental particles, that is electron and a proton and a neutron, which cannot be further divided. Remember that Greeks had a point of view that atom cannot be further divided, and then J.J. Thompson went on to prove that atom can be further divided into electron and proton part. And in 1930 we then knew that atom has three basic constituents, can be divided into three parts, that is electron, proton and neutron. So this fascinating journey has just begun, and we now know that there are three fundamental particles in around 1930s, and there is a Bohr model, there was a J.J. Thompson model, and then there was a Rutherford model, and now there is a Bohr model, which explains that how these three particles live inside the atom. So in future lectures we will then be discussing about the new particles discovery. We will move ahead after 1930 into further time, and we will talk about the theories and the particles and the theories explaining them. With this, I thank you.